Hi guys, welcome back. Hope you're well. Hope everything's going smoothly for you. Wish I could see you all in person. Um, we're going to start into a really important section of chemistry, and that is discussing the mole and how chemists use it every single day. This is a super critical part of your education for chemistry, and I hope we can make this work over the internet. You're already familiar with the mole, of course, because we had our silly fun day back in October. So hopefully you remember what the number value is for a mole. We are going to be talking lots more about it. If you wanted to count the amount of sand in a sandcastle, the number of grains of sand in a sandcastle, it would be really ridiculous and take a long time. So what we would probably be able to do a lot easier is count out 10, 100, 1,000 pieces of sand and weigh them, then weigh the mass of the sandcastle all together, and then use the mass of a few pieces of sand to calculate the number of pieces of sand based on the mass. Now, that might not make a lot of sense right this second, but hopefully it will soon. There's 3 different ways that we can measure the amount or quantity of something. You've done this before. You can go buy pounds of birdseed or dog food or cat food or whatever. You can buy gallons of paint, so that's volume. The pounds would be mass. And then, of course, you could have an absolute count, like if you bought a box of deck screws or something, that would have a specific number of screws in the box. So those are 3 methods of counting, believe it or not. You can count atoms knowing the weight of one of them and then comparing it to the whole group. So going back, maybe this is easier to comprehend than the sand grains. Paper clips. We buy paper clips in boxes. Probably most of the time it's boxes of 100. Don't know for sure, but lots of the ones that I've seen are. There is nobody at the paperclip factory sitting there and counting out all the paper clips 100 at a time. That would be way too labor intensive and take too long. Same kind of thing. Gotta go back to chocolate. With chocolate chips, there's nobody in the chocolate chip factory counting out the number of chocolate chips that need to go in the bag. The main reason, of course, is because they'd eat half of them before they ever got them in the bag, but maybe that's only just me. But you get my point, right? Paper clips can be assembled into their containers that are sold that they're sold in by weighing out a set mass of paper clips. There's nobody, well, maybe there's a few of you, but there's very few people on the planet that are going to open up their box of paper clips and count and be sure they got exactly 100. But maybe you feel the need to do that. I don't know. Chocolate chips, of course, are done by mass, so you've probably seen how it's made. There's a conveyor belt, and the little baggies go down the conveyor belt, and all the chocolate chips go in, or all the paper clips go in the box. There's a little weight sensor underneath that says, yep, that's enough, move on, and away they go to be shipped to market. All right, you're going to need your calculators for quite a while to come, so be sure to have those with you. These first problems aren't that hard, but very shortly we jump to scientific notation, so be ready. One of the types of problems that we have to do, and this really honestly isn't that much after this chapter, but sometimes we need to get a mass from counting out pieces. Now, they chose to do apples, so that's fine, and we'll use this because apples are pretty well familiar to everybody. So let's go. When you read this question, it says, what is the mass of 90 average-sized apples if a dozen of the apples has a mass of 2.0 kilograms? So chemistry, in addition to dealing with little tiny things that you can't see, brings in all those fun word problems from your math classes. There's a technique, a good easy trick that I'm going to hammer into your skulls to help you know how to solve problems perfectly every time. What I call the beginning of this problem, where it says, what is the mass? That's the asked for information. Our book uses the term wanted. I prefer asked for. It really doesn't matter. You get the idea. The next thing that you look at is if there's any numbers. And honestly, if you can, the best way to do word problems is to actually physically circle things. Obviously, probably not a good idea in your textbook, but if it's something you can write on, do that. So what's the mass of 90 average-sized apples? Okay, that's what they're asking for. And they give you some information. They're saying 1 dozen of these average apples has a mass of 2 kilograms. Okay, so at first glance, it doesn't seem like there's quite enough information. We don't know how many a dozen is. Or wait, do we? Well, of course we do. You know that a dozen is 12. This is what's called a conversion factor, or a ratio. There's 12 apples per 1 dozen. Obviously, you cancel that out, and you know that in place of the word dozen, you can substitute 12 apples. Well, that's all great and fine. So this is one way you can solve this type of problem. 2 kilograms per 12 apples, that's proportion, is the same as or equal to some unknown number of kilograms per 90 apples. Now sometimes these are really obvious, it's like it's 48 and just have to multiply by 4 because you can do that kind of math in your head. You're all good at that. But they made this one a little difficult on purpose. So 2 kilograms per 12 apples is the same as some unknown mass for 90. Well, you can use your handy dandy old friend cross multiplication, which of course is just cheater's way of doing algebra properly, but most of you have done these kind of proportion problems before, I'm sure. So 12x is equal to 180, and of course you can push buttons on your calculator and you would figure out that x, 90 apples, is going to mass at 15 kilograms. Right? That's one type of problem. Another problem that we're going to jump right to is we're going to talk about words that mean numbers. There's counting words. Decade, you all know, is 10, but it's for a specific thing, of course. It's 10 years. 2 could be 2 gloves, 2 socks, 2 shoes, 2 pieces of paper, 2 pencils. But the number 2 means pair, or the word pair means 2. Of course, we already talked about 12 is a dozen. Some of you may know that the word ream is actually a number as well, but it's for a very specific purpose, kind of like decade, and that's for 500 sheets of paper. So the average size package of average weight paper is 500 sheets. That's a ream. Some of you know that 144, well, that's 12 squared, and that's also known as a gross, and you can have a gross of anything. Pencils comes up a lot for some reason, but of course chemists prefer to use the number mole. That's mole of any substance, as you know, contains 6.02 times 10 to the 23rd, and here's where our book gets a little wonky, representative particles. 6.02 times 10 to the 23rd things, grains of sand, pencils, pennies, that's a mole's worth. For chemists, it's been defined explicitly as the exact number of carbon-12, remember that's one of the isotopes of carbon, in 12 point gajillion zeros grams of carbon-12. So exactly 12 grams of carbon, 12 has exactly 6.02 times 10 to the 23rd, in this case atoms. This is a video we saw back in October. There's a space for you to re-watch it and write a little comment or two on your assignment sheet. Let's go back to that representative particles terms. Most of the time when we're talking about elements, we're talking about atoms. Okay? Not all elements. Remember, there's lots of diatomic ones and octatomic ones and all sorts of weird things. but most elements run around as individual atoms. Then molecules. That term is supposed to just be used for our covalently bonded compounds. Formula units is the term we're supposed to use for ionic compounds. Honestly, I don't have any problem with you using those two interchangeably, but just heads up. And then ions. So when ionic compounds go into water, they dissociate, and you have sodium ions and chloride ions. For example, when salt dissolves, you can count the number of ions as well. So every type of substance will have its own particular type of representative particle. 1 mole of any of those is 6.02 times 10 to the 23rd of those things. Again, the mole is the Système International, the metric system unit for measuring the amount of a substance. And our good friend Amedeo Avogadro, as you also know, is the person who first put forth the concept of something called the mole. And at the time he was working, Avogadro was working with gases. That was a big field of research back in the late 1700s, early 1800s, the new cool thing to do. And what he decided, based on how things were combining, if you had equal temperatures and equal pressures for those gases, an equal volume, a liter, 2 liters, whatever, would have the same number of particles of their particular gases. That's known as Avogadro's hypothesis. If you have a liter of helium and a liter of neon, even though their atoms are different size, both samples will have the same number of particles in them in that 1 liter bottle if they're at the same temperature and pressure. Now, one of the hard things to do is converting. And again, we're not going to do too much of this, but we have to do a little bit. One of the types of problems is converting from a number of particles, whatever they are, into moles of those particles. And so this one says 2.80 times 10 to the 24th atoms of silicon. It's really irrelevant what the element is, but they want to know how many moles. And of course, that's our asked for unit, and atoms are what we've been given. The packing units around when you're doing calculations is a bit time consuming. However, it will save you over and over and over again if you keep the units with the numbers. You'll be able to solve any problem. So again, you're given atoms of silicon. You're asked to find moles of silicon. And the book has this weird looking conversion ratio thing. I'm going to try and explain it a little bit better for you than this little diagram. So again, atoms, moles. You're given atoms, you're asked for moles. You're going to want to make a conversion factor like we did with a dozen apples, 12 apples per 1 dozen. You're going to want to make a conversion factor to do your calculations. So, same problem. Here's what we start with. Always write down what you're given first. Then come up with a conversion factor that has the asked for unit on top and the given unit on the bottom. In this case, the asked for unit was moles. The given unit was atoms. Notice the dividing line here. One of these is the same as 6.02 times 10 to the 23rd of these. Remember that 2.80 times 10 to the 24th atoms can be written over 1. So now you have 2 fractions. Whenever you're doing math problems in science, units on top of 1 fraction will cancel if you're multiplying or dividing, units on the bottom. You're left with moles in the numerator, the unit that you want in your answer. I'll give you a second or pause right now, and hopefully you all got 4.65 moles of silicon. All right, here's another one. Same kind of thing. 2.17 times 10 to the 23rd representative particles. Well, you might remember that bromine's a diatomic element. That's why they can't put atoms, but whatever. Again, moles are being asked for, and representative particles have been given to you. So write down your given information, so RPS, representative particles. And then you need a conversion factor that has the asked for unit on top and the given unit on the bottom. Recall, of course, that this whole thing can be written over 1. It doesn't change anything. It just makes canceling units more obvious. 1 mole anything, no matter what kind of particle it is 6.02 times 10 to the 23rd. So notice when we're going from particles to moles, we're dividing by 6.02 times 10 to the 23rd. Hopefully you got 0.361. I forgot to pause, sorry. And that really should be BR sub 2. All right, you can also go the other way, okay? Having moles and changing them into particles. And it doesn't matter if it's atoms, molecules, or formula units, or ions. This time, instead of dividing by 6.02 times 10 to the 23rd, we're going to multiply by it. It's in the numerator. Again, the asked for unit goes on top. The given unit, moles, goes on the bottom. So this one has a little extra trick to it. Take a second to think about it. How many atoms are in 1.14 moles of SO3? Hopefully some of you realize that SO3 is not an atom, right? It's got an atom, it's a molecule. It's got an atom of sulfur, excuse me, and 3 atoms of oxygen. So that means there's 4 atoms in every single one of these, so that's a little bit tricky. So we just have to put in an extra conversion. Still asking for atoms. We've been given moles. And again, it's moles of molecules, and they're asking for number of total atoms. And you have to recall that the atoms, there's 4 of them in an SO3 molecule. So my setup looks something like this. Start with what you're given, the 1.14 moles. Put in a conversion to get rid of moles, so moles on top, moles on bottom. We're left with molecules. Oop, forgot a fraction line there. And then we want to get rid of molecules, so molecules has to be on the bottom. We're trying to find atoms. Atoms have to be on top. And hopefully you can calculate 2.745, which is way too many significant digits, of course, times 10 to the 24th atoms. Don't freak out about the math and make a mountain out of a molehill. So another thing that we do all the time, this is the thrust, the most important part of this section, honestly, is how we can find the molar mass of an element or a substance. Remember, when you look at the periodic table, there's lots of information for each element squared, atomic number, which is the number of protons, good job, the symbol for the element, these are the electrons in the layers of the element. This is, of course, its name, and then this is the weighted average mass. Remember, this is all the isotopes, the different masses of the different isotopes by their percent natural occurrence. All of the substances are compared to carbon-12. They've gone back and forth on which element to use as the basis. They tried hydrogen, they went to oxygen, and they've been back and forth with carbon a couple times. We are using carbon-12. AMU is atomic mass unit. If you took one carbon-12 atom and divided it into 12 pieces, you would have 12 atomic mass units. Helium has an atomic mass value roughly of 4. It would take 3 helium atoms to equate to the mass of 1 carbon-12. That's all we're referring to, is how particular elements, atoms, compare to carbon-12. Every substance has a different atomic and then, for compounds, molecular mass. Carbon-12, 1 mole of carbon-12 is exactly 12 grams. A mole of sulfur atoms, 32.1. A mole of mercury is 200.6. A mole of iron, 55.8. You might remember the beakers I had out during mole day. Again, everybody's comparing to carbon-12. And it turns out, since an atomic mass unit, there's 12 of them in carbon-12, and carbon-12 weighs 12 grams per mole. One atomic mass unit correlates to, for an atom, correlates to 1 gram of a mole's worth of those atoms. So AMU compares to one atom element to one carbon-12 atom. Grams are the mass of a mole's worth of that element. I will call it molar mass almost all the time. So those numbers on the periodic table not only refer to individual atoms of the elements, but also to moles of those elements. So if we compare carbon and hydrogen, we can do it atom by atom, 2 atoms, 10 atoms, 50 atoms, a mole's worth of atoms. It doesn't matter. Very most important thing, how do you calculate the molar mass of a compound? We need to know how to do this because chemical reactions occur atom by atom reacting with each other. We have to be able to count them, which of course is impossible because we can't see them, but we can weigh them out, mass them out, and get enough information to do our calculations. Very, very simple. Write these steps down. To calculate the molar mass of a compound, you first have to know the molecular formula, which we've learned how to do. Once you have that, you look at your periodic table and find the grams that are listed underneath the symbol for each element. Multiply each of the elements by the subscripts in their chemical formula, if there is one, and then simply add them all together. It's really quite easy. So sulfur trioxide, the substance we were looking at earlier, we know is composed of 1 sulfur atom and 3 oxygen atoms. 32.1 AMU, or 32.1 grams per mole, is what's listed for sulfur. 16.0 for oxygen. Now, when you look at your periodic table, it's going to be 15.999 something. Okay, and this might be 32.08. I can't remember off the top of my head, but just round it for right now to the tenths place. Sometimes it's beneficial to go out to the hundredths place, the pennies place, but most of it's going to come out pretty straightforward and pretty easy. So 32.1 plus 48 gives you 80.1. And it really should be AMUs. It's also 80.1 grams for a mole's worth of this molecule. Glucose, water, paradichlorobenzene, they all have different molar masses. 180 grams per mole for glucose, 18 grams per mole for water, and 147 grams for paradichlorobenzene. So find the molar mass of phosphorus trichloride. I should make you name it too. Phosphorus on your periodic table is 30.97. Chlorine is 35.45, but there's 3 of them. So we're going to have to multiply the individual mass for chlorine times the subscript 3, and then we just simply add them all together. And that, my friends, is it for today. This is a super important topic. I hope it makes sense, and I'll see you next time. Take care.